Welcome back. Thank you for joining me for 6-3, binomial radical expressions. So today we're going to start by talking about addition and subtraction of radical expressions. Now this is something you started seeing in Expo, but we're going to take it a step further today. So you should already know you can only add and subtract like radicals, meaning they have the same index and same radicand. So that n value, the index has to be the same, and you need the same number inside the radical in order to perform that addition or subtraction. So the steps to adding and subtracting these like radicals. First, check to see if the terms are like radicals. So are they the same index, same radicand? Second, simplify the radicals if necessary. You won't always have to, but sometimes you will. And then third step, add or subtract the coefficients outside of the radicals, but do not change the radicand. So for example here, when you see square root of 2 and 3 square roots of 2, you have one of them here, 3 of them there, so they add to 4. Or here, cubed root of 7 minus 5 cubed roots of 7, so 1 minus 5 would give you negative 4 square roots of 7. So all you're doing is adding and subtracting the coefficient, but leaving the radicand itself alone. Now to show you some examples of ones that don't work. All right, so right here, you can see square root of 7 and square root of 5. So in this case, those two terms cannot combine because they have a different radicand. They have a different value inside the square root. So these are not like radicals and cannot combine. Same thing here. Well, this time the 5's match up. However, the difference is one is a cube root, the other is a square root. So again, that leads again to not being like radicals, and those would not be able to be added or subtracted. Now, obviously, the goal of today is looking at ones that can be. So this is going to be our focus. Ones that look like the 3 on top, where these actually can end up combining. So I want you to look. 3 square roots of 5 minus 2, square roots of 5x minus 2 square roots of 5x. So notice the index is the same, they're both square roots, and the radicand is the same, both 5x. So we're starting with 3, we're subtracting 2 away, so that's going to leave us 1 square root of 5x. Remember, all you do is subtract the index, or subtract the coefficients, but you leave the radicand alone. Now, in this instance, however, you don't really need to show the 1. So if you just call that the square root of 5x, that is perfect as well. You never really need to show that 1 out front. Looking at our next example, 3x square roots of xy plus 4x square roots of xy. So again, both square roots, both have the same radicand. So 3x plus 4x, well, combining like terms, that gives us 7x. Then again, the radicand would stay alone, or would be left alone, and you would have square roots of xy. Then this one, 17 fifth roots of 3x squared minus 15 fifth roots of 3x squared. So in this case, both have an index of 5, both have a radicand of 3x squared, so these are in fact like terms. So we're going to take the 17 minus the 15 to get 2, and then everything about the radical stays exactly the same. All right, now looking at further examples. So there are some we're going to have to simplify the radical first. So let's take a look at this. Now for both of these, what I recommend is having that little power chart out again, because that's how you're going to see what numbers you can pull out. This first example, the square root of 12 plus square root of 75 minus square root of 3, that one is focusing on square roots. So you would look for the second column. And you would see 12 can be split up into 4 times 3. Again, you're looking for that largest perfect square. The 75 can be split up into 25 and 3. And then we don't really have to do anything with the square root of 3. Well, this becomes 2 square roots of 3, 5 square roots of 3. That one, again, is the same. Well, notice once you simplify it, now the radicands are all the same. They're all square roots of 3. So in this instance, now after transforming it, we're going to be able to add and subtract these. So I have 2 plus 5, then minus 1. That's going to give me 6. And then the square root stays the same. Okay, you don't change the index or the radicand when you're adding and subtracting these square roots. Now, cubed roots work exactly the same way, except this time, to find the numbers that you're pulling out, you're going to be looking at the third column, the third power. And what you'll notice, 250, you can pull 125 out of that. So that's what's up into 125 and 2. 54, looking for what pulls out of that, you're going to see that splits up into 27 and 2. 16 will split up into 8 and 2. All right, so I found all the perfect cubes that pull out of each of those numbers. So cubed root of 125, we know is 5. It was why we broke that out. Cubed root of 27 is 3, which again is a nice number, which is why we pulled it out. Cubed root of 8 is 2. So now once again, by simplifying first, now all of the radicals are like radicals, and we're going to be able to add and subtract them. So I have 5 plus 3 minus 2 gives me 6. And then you just write out the radical. Remember, the radical doesn't change in these examples. All right, so let's wrap up with our word problem. So, an architecture problem. In the stained glass window design, the side of each small square is 5 inches. Find the perimeter of the window to the nearest tenth of an inch. All right, so every square has a side length of 5. So that means when I'm looking at this chunk here, if each side length of the square is 5, that means both of those are 5. And I have a right angle there. So I want you to consider, if I know those two sides, I know both of them are 5, and I have a right angle. You guys learned years ago how to solve that. Remember, that is going to be an instance of Pythagorean theorem. A squared plus b squared equals c squared. And remember, it's always a hypotenuse. It's always that side opposite the right angle. That is our c value. So I'm going to let that be c. So that means if I want to know that length right there, I just plug it in. 5 squared plus 5 squared equals c squared. Well, 5 squared plus 5 squared, 25 plus 25 gives me 50. And now square root both sides. So c is going to be the square root of 50. However, that's not simplified. 50 can break up into 25 and 2. So really, if we're talking about simplified radicals, it's going to be 5 square roots of 2. Now, we don't want just one value, however. It wants to know the perimeter. So let's see. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those lengths around the perimeter. So I'm going to take that and multiply it by 10, because that's going to give me the entire way around the figure. And when I do that, I'm going to have 50 square roots of 2. Now, as nice as it is to have an exact answer, I don't like rounding to the very end of my problems. But as nice as this exact answer is, if you want to know how much that perimeter is in a world context, real world, having 50 square roots of 2, that's really not telling you very much. So that's why it's telling you round it to the nearest tenth. All right? In real world examples, having a decimal answer means a whole lot more than a radical answer. So if you type that into the calculator, you will get 70.7 inches. Okay? That is what your final answer is as a regular decimal. All right, so that is going to be all for our notes today. Thank you so much for joining me. Please make sure that all of these are filled in and finished, and then come back to class ready to do some more practice work.